talk on rational points on certain curves. So, Stevan, please.
Thank you very much for the introduction. It's a shame that I cannot be in person in Moscow, hopefully in the future. And yes, I should share my screen and start. So let's see. Is this good enough? Can you see it well?
Yes, perfect.
Okay, thank you. So today, yes, I will talk about rational points on certain curves. Well, I will advertise this area of mathematics mostly. And well, we can start with recalling some well-known things about rational points on curves. So today, well, curves will be nice in a sense. They will be smooth, projective, and geometrically reducible. Well, of course, algebraic varieties of dimension 1. And well, G will be reserved for the genus of the curve. And well, we recall well-known thing that if we have a curve of genus 0, then over an algebraically closed field, it's isomorphic to the projective line. But over Q, things can be more interesting. For example, there are curves that have no rational points. For example, this well, circle of the radius square root of 3, or there could be infinitely many rational points. And well, I think the most important example is the unit circle, because it parameterizes Pythagorean triples. And then things get more interesting in higher genus, for example, in genus 1, and well, to avoid worrying about empty sets. So we assume that there is at least one rational point. Then we can create a group law on curve C, and we call C an elliptic curve. And then Mordell proved that this group law is, well, this abelian group law forms a group of finite rank. So this group of rational points is isomorphic to Z to the R, where R is called the rank of this elliptic curve, plus a torsion subgroup. And both, so when we have an elliptic curve, then both problems are interesting. For example, it's still somewhat an open question if we can compute rank of an arbitrary elliptic curve. Well, there are algorithms, but in practice, none of them work in all cases. And also, well, there is an interesting question of determining this torsion subgroups of elliptic curves. And we will see, well, that was completed by Maser for the rational points, and we will discuss it soon. And then mostly we will be concerned about curves of genus at least 2, because then the set of rational points is finite. That is famous Falting's theorem. However, this theorem is ineffective, meaning that from its proof, we cannot find any way to compute explicitly the set of rational points on C. And this is still a research in progress on how to make Falting's theorem effective. But we will talk about some concrete method, well, the method initiated by Chabauty and some variants of it. So today's goal is to describe some methods to explicitly determine rational points on curves. And before we do that, well, obviously we need some motivation. And for example, I mentioned Maser's theorem. And so if we want to classify points of order n on elliptic curves, then for example, we can consider classes of isomorphisms of elliptic curves E and points of order n on them. And we consider them together because then we can parameterize them using some moduli spaces. And well, this is the simplest case. And there is a curve that parameterizes such classes. And if we work over an algebraically closed field, K bar, then there is a curve of y1 of n defined over Q, such that for any point on this curve corresponds to exactly one class of isomorphisms of elliptic curves with an n torsion point on it, but defined over this algebraically closed field. And of course, if this class has elements defined over K, so if E and P are defined over K, then the point will be itself in K, and we have a conclusion that follows. So if there are no points on y1 n of K, then there are no elliptic curves with an n torsion point defined over K. But
sorry, I lost. What is y1 n?
This is a curve that parameterizes these isomorphism classes of pairs.
Mm-hmm.
So there is an action of some congruent subgroup of on the upper half complex plane, because over C we can see elliptic curves as a tori. We can see elliptic curves as tori, and then we can parameterize them using complex numbers. And then if we have a point of, well, if we use the standard representation of tori from topology, then points of order n are form the lattice inside of a square of n times n lattice. And then we use this parameterization to define charts on a complex half plane and to obtain the equations of a curve, but I wanted to avoid explicit equations of curves here. So does this answer your question? Okay, thanks. But the problem is that these curves are still not very nice, and especially, well, we want to work with nice curves, so then we compactify these curves to obtain curves, well, we call them x1n. These are smooth and projective curves. So these will be our nice curves. And for example, x1n consists of points on y1n. So yes, maybe I should have written it that x1n is y1n plus some cusps that are obtained by this compactification. And if x1 of n contains only cusps, it means that y1 of n is empty, and there are no elliptic curves with n torsion defined over this field K. And for example, this is one of the most presented examples about Mazur's theorem, that x1 11, well, when we compute its equations, we obtain that it's an elliptic curve, and it has rank 0, so has only 5 rational points, and all 5 rational points are cusps, so there are no elliptic curves of over Q with an 11 torsion point. We will not discuss Mazur's theorem, but some extensions of it later. And
but maybe, in fact, this is very interesting concerning this. So
yes,
let us consider all possible value of this number n of this order, right?
yes.
So we can find all such n that there exists an elliptic curve over Q such that there are rational points of this order, right? Say for 11, there is no such curve.
Yes.
Is it known for which n there are such curves and when there are no such curves?
Yes, so this is for n less or equal to 10 or 12, there are elliptic curves over Q with an n torsion point. And that's and that was over Q. Nowadays, it's interesting. Well, it's a very interesting question to extend it for small degree number fields. And well, there was a recent result last year that they computed the classification of all possible torsion subgroups of elliptic curves over cubic fields. I will tell something about it later. But this was one motivation why we want to study rational points on curves, because we can parameterize some important objects from other areas, and by determining rational points we can conclude some very good conclusions. For example, here it was used to describe possible n torsion points on elliptic curves. And well, we will see soon some other examples. So, may I go on, or?
Yes, sure, sure.
Okay, thank you. And then, well, the first, if you consider the first example as somewhat of cheating, because we use rational points on curves to obtain some information about curves, so then we can consider some example from arithmetic dynamics. And for example, let's consider a quadratic polynomial z squared plus c, where c is any rational constant. And then we can iterate this polynomial. And so you can see the second iteration of this polynomial, and so on. And so we, in some sense, we create a dynamical system, and then we want to see if there are fixed points of this system here, so that are there fixed points of the nth iteration of this polynomial. And well, as usual, if n is the smallest number such that g iterated n times of z is equal to z, then n is called the period, and z is called the point of period n for this polynomial g. And for example, for n equals 5, it's interesting because then the only smaller periods that can make sense for n equals 5 are one periodic point. So all fixed points are, of course, fixed by, if we iterate g5 times. For example, if we consider n equals 6, then all 2 periodic points are also a subset of 6 periodic points. But here, since 5 is prime, then it's somewhat easier. And this is a 5 of z and c is indeed a polynomial, because then if something vanishes in the denominator, then it's a fixed point. So it's a fixed point of fifth iteration. So this is indeed a polynomial in z. And if something is a fixed point of fifth iteration of g, then this is 0. So this curve describes all points that are fixed by fifth iteration of g, and not ones that are fixed, well, maybe not ones that are fixed by g itself.
Steven, I'm sorry for interruption, but I would like to encourage our participant to ask questions, because I see that this is something beautiful and understandable. But me personally, I cannot follow so quickly. For example, I don't understand what is your iteration. Am I right that you substitute polynomial as a variable in the same polynomial, right?
Yes.
So the degree grows and grows. How
Yes.
can you get that again after several steps?
Oh, well, then you get a polynomial equation. For example, if we consider second iteration, then we want to solve z to the 4th plus 2c, z to the squared plus c squared plus c equals z. So that is, they are not equal as polynomials.
You are looking for solutions of these equations, right?
Yes, yes. So that is, oh, sorry, yes. So then this is not as polynomials, but this is an equation that we want to solve.
I see. And you're interested in whether there are solution or no solution, right?
Yes, in both.
So if we have solution for n and we don't have solutions for m smaller than n, then that is called a point of exact period, right?
Yes.
Or
but this is for a specific z. So then this is z is fixed. Yes.
I see. Okay.
And well, most of these won't be a periodic point of, of any polynomial.
So here z is not a variable. This is some value.
Oh no. Yes, maybe I should. So z is a variable here, and yes, maybe I should have written here z naught to distinguish.
Yes.
And here it is a variable again. And the good thing about periods is if we have a period of, well, degree 5, for example, then if we go from 1 to 2 to 3 to 4 to 5, then we go back to 1. So it's the same if we start from 2 and go to 3, 4, 5, 1, and 2. And that is the explanation that this curve actually has an automorphism, because if z is a 5 periodic point, then its iteration z squared plus c is also a 5 periodic point. And that is something very useful in this case, because curve this curve C1 of 5 has large genus 14, and then we want to identify all periods together to decrease the genus of our curve, and then we consider curve that has significantly less genus 2. So we define a quotient curve where we identify all points in the same orbits. And then C naught of 5 is a nice curve. But we need to be careful here, because we here obtain all 5 cycles, so orbits of 5 periodic points, but none can guarantee that pointwise these points belong to Q. This is the same thing as with the divisor. So this is fixed by the action of Galois, of the Galois group of Q, but it doesn't have to imply that points corresponding to 5 cycles are pointwise rational. And we will see this again when we talk about symmetric powers of curves.
Yeah, I wanted to ask, so this is like a branched covering of this C05 curve, right?
Yes. Okay. And well, here we use this C naught because we can find an easy equation for it. So this is a hyperelliptic curve of genus Stoll. And if we can determine rational points on it, we can then check which ones correspond to rational periodic points and which one don't. Well, in this case, it will turn out that none of rational points on C05 correspond to rational periodic points. But this was another illustration how we end up with a problem of determining rational points on curves. And there is one maybe not so important example, but somehow it was a miracle when I read it. So I have to advertise it. There is a simple question. If we consider one rational right triangle, so this is a right triangle that has rational sides, and one rational isosceles triangle, then the question is, can they have the same area and the perimeter? So this is a simple geometric question. And of course, well, we can write equations for it. So if we consider two triangles, we can scale them, and area and perimeters will, well, the ratio of their areas and perimeters will stay the same. Well, if it is equal, not. And then, so we only need to consider one scaling coefficient, that is k. And here we recall that we parameterize rational triangles, right triangles, by 1 plus x squared, 1 minus x squared, and 2 times x. So this comes from the Pythagorean triples m squared plus n squared, m squared minus n squared, and 2mn. So this is for integers, and this is the corresponding shape for rational triangles. And since we already have a scaling by k here, we don't need to scale the isosceles triangle. And how do we parameterize them? Well, we simply divide it by the central height to two right triangles. So this is again parametrization coming from right triangles. And there are two cases whether the height is equal to 1 minus x squared or 2y, but two cases are isomorphic, so this one was easier to write, and we will consider this.
Steven, I'm sorry again. A right triangle means with right angle, right?
Yes.
And what is isosceles triangle?
If two
Right
sides are
sides.
equal.
If two sides are equal. Okay, I see.
Yes.
My question, I have a question too. For an isosceles triangle, you assume that its height is rational. Is the letter
yes.
U?
Sorry. Yes. Thank you for that question. Not well. We don't assume it from the beginning, but since we know that the area of the other, if we consider two triangles with the same area, the area of a rational right triangle is a rational number, and then the area of the other triangle is again a rational number. So then the heights will need to be rational.
Okay.
But in general, we don't. Yes, thank you for that question. Yes, so that is a very good point. That so we had to prove in advance that a height of this isosceles triangle is rational, but it follows from the assumption that the area is rational. And then I will skip the derivation of it, but so we can see, so this is an area equation and this is a perimeter equation. And I guess the area equation is scaled by 2. And then, for example, we can re-express x using k and replace here, and we get an equation in 2 variables that after some algebraic transformations lead to this curve. And then we want to, as all transformations were rational, so we want to compute rational points on this curve. And if we, so this u is the same as this u, and when we obtain all rational values of u, then we, doing the reverse transformations, we can conclude what k and x can be. And we translated one geometric problem into computation of rational points on some curve that is again hyperelliptic of genus 2. And the last two curves will appear again soon. So that was some kind of motivation that rational points on curves can arise in distinct areas of mathematics, and that is one reason why they are so important. And then we will start with describing some methods to determine rational points. But before that, so note that this is in 40s. So Chabauty in 40s proved that for a nice curve of a genus at least 2, that satisfies the condition that its Jacobian has rank over Q less than its genus G, then the curve, then the set C of Q is finite. So of course that is weaker than Falting's theorem. Falting's doesn't need any condition on the Jacobian, but it was 40 years before Falting's, and this was the biggest step in proving the so-called Mordell's conjecture, nowadays Falting's theorem, until Falting's proved it. And here I want to point out the heuristics, or where is it? Okay, then maybe we can see the diagram. So we start with points of rational points on C, and then we embed them via the Abel-Jacobi map. We can choose any Abel-Jacobi map to J of Q, and then we also embed C of Q inside of CQP, and so these are points over p-adic field. And we can see it again, we can embed CQP inside of JQP again using any Abel-Jacobi map. Well, we should use one that comes from a rational point so that we have a commutative diagram. And Then J of Q is, as Mordell-Weil theorem says, a finitely generated abelian group, and J of QP is a p-adic manifold. So if we want to see J of Q as a p-adic submanifold, well, we need to compute its closure, p-adic closure. So this is a, oops, what did I do? This is a p-adic closure of JQ inside of JQP, and then this is a submanifold of J of QP. And then for, of course, curve is something of dimension 1, and we can prove that if the rank of J of Q is equal to R, then the dimension of JQ bar as a submanifold of J of Q is not greater than R. So we get something of dimension 1 and something of dimension R inside of something of dimension G. And then if R is less than G, then for dimension reasons, we expect that the intersection of CQP and JQ bar within JQP will be finite. And that's what Chabauty proved. So to recall, then we have a space of dimension G, and inside it we have something of dimension 1 and something of dimension R. And then these two spaces intersect in something, we'll expect that they intersect in something finite. And that is what Chabauty proved, but we will prove later the effective version of it, so we don't need the proof right now. But I hope that you, so that you remember the main idea for the Chabauty was that, well, this condition that R is strictly less than G means that two submanifolds intersect in a finite set of points. And then,
and is there any sort of modern proof of this fact using like intersection theory and some sort of shift lemma? I don't know.
Oh, to be honest, I don't know, because, well, I mostly cared about effective proofs, and so here we'll see one that uses p-adic integration on curves. Well, I would suppose that there should be some other proofs, but simply I haven't seen them. Sorry about that. And so then we recall that we have for any nice curve defined over field K, we have a space of regular differentials. And for example, if we have a hyperelliptic curve, then we can take the regular differentials of the shape dx over y and up to x to the g minus 1 dx over y. So note that there are g of them in total, because that's something that we know that the dimension over k of regular differentials is exactly g, of course, over well, no, that's, let's just continue. It's already 5:30. We have this is a standard thing that I don't want to spend time on, that if we have a curve and it's Jacobian J, then the spaces of regular differentials are isomorphic, and we obtain them by pulling back the Abel-Jacobi map. And later we will identify these two spaces to avoid some unnecessary notation. And the good thing is that finally we are approaching the definition of some p-adic integral that has many nice properties, even nicer than a usual complex integral on surfaces, as we will see soon. So we take all regular differentials and all elements of the Jacobian, and then we define an integration of regular differentials over divisor. So we see elements of the Jacobian as divisors of degree 0, and we integrate over them. So this integral has many nice properties. The first one, and the most important for, well, applications in computing rational points, is that this integral is locally analytic, meaning that we can expand this integral when we use coordinates at points as a converging power series over periodic numbers. And converging power series over periodic numbers have many nice properties. So that is the most important property of this integral, one of. Then, of course, what we want from integration, we want it to be additive on end points. This means z linear in D. So if we change point, well, it is additive in end points. It is linear in the integrand. So it's QP linear on the left, meaning in omega. And we can describe its kernels. So it's we don't need to take care of it now, but we can easily describe kernel from the left and from the right. And one of the most important things is that, well, we will recognize this as a change of variables. So it's still true for Coleman integral that if we consider a map morphism of curves that induces a morphism of the Jacobians, here intentionally we'll use the same letter, then we can compute, well, integral on one Jacobian going to another one and vice versa. So as we can see, all properties from calculus are there, and we will see one important property very soon. We want to integrate on curves, not on Jacobian. Well, we want to integrate on Jacobians as well, but also on curves. And then we can define integral between 2 points on a curve as a, so P minus Q is a divisor of degree 0. So we can see it as an element of the Jacobian. And then we use it to define integration on a curve. And one thing that we should emphasize here is that this integration does not depend on paths. So unlike the complex case where when we integrate over some Riemann surfaces, we need to be careful how we go from P to Q. Here it doesn't matter. So in this sense, I say that this integral is better than what we have learned in calculus. And it still has other properties that we expect from integration. And in some cases, this integral is very easy to compute. And in general, when we want to compute rational points, if you try to solve some Diophantine equations when, well, sometimes in past, then maybe you recognize the trick that if your equation has no solution modulo some prime p, then it won't have integral solutions. And here, well, we will use the same strategy. So we will often look at the reduction of our curve modulo p. And of course, if the reduction of modulo p is empty, then there could not be any rational points. So it's important to introduce the residue disk. So the residue disk is a set of all points on a curve, well, over QP that reduce to the same point. And then we need to introduce some more notation that if we know that if, well, P curve is smooth, so then we have a uniformizer at P. Its local ring has a maximal generator of maximal ideal. And when we take a uniformizer T, we can reduce it to a uniformizer. But if we can reduce it to a uniformizer at the point of the reduction mod P, so P bar, then we call this a uniformizer, a well-behaved uniformizer. And these uniformizers are important because they describe residue disks in a very nice way. They provide a bijection between the residue disk of P and P times ZP. Because if we start with some point P and all points in the same residue disk have to differ from P by something divisible by P. So this is not a surprise. And in this case, if we are in the same residue disk, so then we call these integrals tiny integrals. We can compute the integral as we learned so far. So integrate it and then replace endpoints. So if omega has a power series a, n, s, and ds, then we integrate it and then just replace p and q. And of course, well, since s is a uniformizer at q, s of q is 0, so we don't need to subtract s of q to the n+1. And this is a way how we compute integrals only in the same residue disk, but it still will help us a lot in finding rational points. So this is why this integral is so useful, because it has all properties that we need. And we will use it to prove the theorem that follows. Are there any questions about this integral? No. Okay, then
this is quite difficult for us, and I see the number of slides you have prepared. So this is slide number, which one?
14, yes.
14 from 61, yes, right?
Yes,
okay,
well,
so let us go further, but it will be much more useful for us to understand some concrete things. And these are pieces of quite distributed information. So, okay, maybe to concentrate on something concrete.
Okay, yes, maybe, well, if we don't make it to, we can stop earlier. That's not a problem, but I wanted to, I hope that at least, well, you could see some motivation, and then we will see. So this is how we introduce the integral. Now we will see the power of this integral. We will prove the theorem and we'll see some examples, and that will hopefully help you to understand better how we use this integration to compute rational points. Okay, then we are back to the setting of Chabauty's theorem, except that here so rank is still less than genus of a nice curve, but then we consider primes of good reduction that are greater than 2 times g. Then there is a bound on a number of rational points. So the number of rational points is less or equal to 2g minus 2 plus the number of FP points. And that is a brilliant result. And we will, so this is a sketch of the proof. So to recall how Coleman used this condition that rank is strictly less than G. Well, that if we have a integration that we have right now, that implies that we can find a non-zero regular differential omega such that integral over all points coming from the Jacobian over rationals is 0. And this is simply, well, this is some formal explanation, but simply, we will see also in the example, we have something of something that is generated by R generators, and we have G conditions, so we get a system with more equations than variables, a homogeneous system, and this system will have a non-zero solution. We will see an example later, but that is the basic idea, so that we can, for example, if we are on hyperelliptic curve, then we want to compute this differential as a linear combination of these differentials, and we integrate each one at each generator. So we get R conditions and G equations and a homogeneous system that has a non-zero solution. So then it follows that we have an analytic criterion to decide whether a point is rational or not. Well, it's inside QP. So for this omega, by definition, integral from any 2 rational points is 0, because this is integral from P to Q. This is an element of JQ. So this is somehow analytic condition that detects rational points, and this is what distinguishes rational points from an arbitrary QP points. And further, for some technical reasons, well, we can scale omega such that it doesn't vanish modulo P. or that it doesn't have a poles modulo P. And then as an idea, so how do we bound the number of rational points? If we start with one rational point and consider a well-behaved uniformizer at T, the strategy is to bound the number of rational points within its residue disk. So if we have a curve C, it will have finitely many residue disks, and we take a point within each one, and then we bound the number of possible rational points. And how do we do that? So if we consider any point that is rational and reduces to the same point as P modulo of this prime P, then we will skip some periodic analysis, but just say that we expand omega as in a local parameter at T, and then estimate the number of zeros of this power series. And that's Strassman's theorem that I don't want to state here. I will say what it is in a concrete example, but Strassman's theorem can estimate the number of zeros of some periodic power series. And in this case, if its reduction modulo P has the first non-zero coefficient with some MP. So this is the first index of a non-zero coefficient. It means that A0, A1 up to AMP minus 1 are divisible by P, and AMP is not divisible by P. Then the number of zeros is at most MP plus 1 inside this residue disk. So we get a bound on the number of rational points within the residue disk of P. And to conclude, we need to sum over all residue disks because all rational points have to reduce to some residue disk modulo P. And then, well, if we forget about MP, if we sum 1 over all points of over FP, we get just the number of FP points. And this also, well, we can recognize this number as an order of vanishing of omega bar at P bar. So then this sum, as omega is also regular, it doesn't have poles. So this sum will be less or equal than the degree of the canonical divisor coming from omega bar. And the degree of the canonical divisor is 2g minus 2. So that is how we get 2g minus 2. And well, we already said that we have the number of FP points. And what will be useful for later, just to recall for Strassman's theorem, if A0 is not 0 mod P and all others are 0 mod P, then there is at most one point in the same residue disk, and we have already P. So the bound is less or equal to 1. So then this set contains only P. This is a starting idea for symmetric Chabauty that we will see later. And maybe we should see some examples to make this concrete. Well, sorry, we need some more definitions. But this is not something that we should be scared of. So this method and this theorem, this theorem and method is very powerful, and we can, well, heuristically, whenever the rank condition is satisfied, we can compute points, rational points on C. Well, this is not proven, but there are no examples with rank less than genus, and that we could not compute CQ. But in most cases, we needed to combine this method with some other techniques, for example, descent or Mordell-Weil sieve. And then we distinguish two cases. When this inequality is actually equality, then we call curve sharp at P because it depends on P. And when there is a P such that we have this equation, we call curve just sharp. So sharp curves for us are ones that this is actually an equality. and these curves are quite rare. So this is one notation, and then if we have an equality here, but we cannot check rank condition, and in practice, if we have curves of high genus, we cannot compute ranks of these curves. It's computationally infeasible at the moment. So if we only see that this equation for proposed number of points, so for number of points that we find is equality, then we call curves potentially sharp curves. And I will get back to this notation later, and to excessive if sometimes it can happen that this bound is not satisfied, and what we can conclude there. So if the number of points that we find is greater than the right-hand side, so it means that this condition cannot be true. So rank is then equal at most, or at least G. But let's go to see some examples. So this is a curve that arises from the triangles problem, and that was a miracle. So this curve has genus 2, and the rank of its Jacobian over Q is 1. And further, we compute that, well, if we take P equals 5, 5 is a prime of good reduction, that there are 8 F5 points, so that it should be F5. And then we can find 10 points on this curve. And then we are done, because the bound says 8 plus 2G minus 2, which is 10. And we found 10 points. So then we conclude that this set is actually the set of all rational points on C. And this is why sharp curves are interesting, well, in a sense they are extremal, but also if we have a sharp curve, so this is an equality, it means that we probably found all rational points. And when we translate, well, just aside, so when we translate these points back to our problem, we conclude that there is a unique pair of triangles, well, up to scaling. And this is a right triangle, and this is isoscales triangle. So they have the same area and perimeter. And so the miracle was that we started from some geometric problem. We translated it to a curve over Q that turned out to be sharp. And there are only a few sharp curves known by now. And that was a miracle to me. That's all I wanted to share here. And this is maybe not so useful to see how this method works. And that's why we have another example. So if we have another, well, this is the second example.
Sorry, and returning to this first example, this nice number 377 and so on, this is the minimal possible solution of this equation.
Yes, this is a minimal integral solution, well, minimal integral sides of both of these triangles.
I see. So this is in some sense the first example of these two triangles with this property.
Yes, so all the others are just multiples of both of them.
Yes, beautiful. I agree. So this is really beautiful.
May I ask a question? How did you get that you have a unique solution up to
So then, for example, well, we can eliminate points 0 plus minus 2 immediately, because it means that U is 0. And then if we go back to our parametrization, where is this?
So which U is it?
U is from the isoscales triangle, but then then we get 1, 1, 2. This is a line, so not a triangle.
Okay.
And recall that U is strictly between 0 and 1 when we do this scaling. So we only consider points that have x coordinate between 0 and 1, so we can delete this one, this one, this one, and infinity as well. So the only U that gives solution is 5/6.
Thank you.
Okay, thank you. Then let's go to the other example, and this is so this is a periodic curve, and again, well, we have a curve of genus 2, and in this case we can do even better. We can explicitly express the abelian group of the abelian group structure of the J of Q. So this is a group with no torsion and generated by the difference of two infinity points. So since this is a monic polynomial, we have both infinity points rational, and of course rank is 1. We have only one copy of Z. And what we can do immediately to reduce everything modulo 3 and to conclude that there are 4 points over F3, 0 and plus or minus 1, and 2 infinity points. And well, if we consider this curve, well, that is something that will probably Magma or some computer system do for us. There is a way, well, the computer systems have their way to search for points. Well, in this case, it's not too bad. For example, maybe you could wonder how someone can find this point on this curve, because it's not obvious at all, but that's usually a task that computer does for you. Well, of course, computers cannot check all rational numbers, but they can do it up to some bound. And in this case, it was easier. So we find 6 rational points and 4 of them modulo 3. So we would like to use theorem for p equals 3 to conclude that the number of rational points on C is at most 6. However, that's not strict. Well, that's not possible at the moment, because we need a condition that the prime that we use is strictly greater than 2 times genus, and 3 is less than 4. So then we cannot use it, and C would like to be sharp, but it's not. And C is not sharp for other primes. So if we consider any other prime, then this bound will be greater than 6, and we cannot find more than 6 points. Well, we will soon prove that it contains exactly 6 points. So then we will imitate the proof, and I think that will help you to see what is going on, because this is an explicit version of the proof of Coleman's theorem. And we can use prime 3 because it's a prime of good reduction. And this is a way how we compute vanishing differentials. So genus 2, we have these two regular differentials and some linear.
Sorry, what is the definition of good reduction?
Oh, sorry, that when we reduce curve modulo p, that we get a smooth curve. Yes, so so we want to work with nice curves, and then we also, when we reduce them, we want also the curves to be nice. So no double points modulo p, and then we are fine. And so here, well, I skipped the computation, but that's, in this case, we concretely know that this curve is generated by the difference of 2 infinities. So we can compute an integral from infinity minus to infinity plus of the first integral and of the second integral, or of the first differential, and here as well, integral from minus infinity to plus infinity of this differential. We get 2 numbers and minus their quotient. This is k, so this number will be, this differential will be vanishing. Because if we integrate omega from between 2 infinities, we get 0. And then we use the additivity that for any other, if we consider any other 2 points, P and Q, then P minus Q is some number times difference of 2 infinities inside this Jacobian. So the integral from Q to P of omega will be 0. And this is a way how we obtain these vanishing differentials. And then we already know that there are 6 points. So let's consider one of them, 0, 1. And we fix a point 0, 1 and consider any point inside its residue disk. So here we see explicitly what it means. So P is in the residue disk of 0, 1. If its coordinates T and S satisfy that T is divisible by 3 and S is congruent to 1 mod 3, and of course the TS is a point on a curve C. And then we use how this integral is defined. So these are properties that we listed. So this is why these properties were important, but let's not waste time on that. So this is an explicit way how we compute it. So the good thing is when we are in the same residue disk, we can forget y coordinates, as you can see. So the integral will depend only on, well, x coordinates in this case, because it's a uniformizer. And when we compute it, we get some power series in T. So we get that 0 is equal to some power series of T, and we want to estimate the number of zeros in T. And that's what Coleman did in the proof of the theorem. And we recall that T is divisible by 3. So we can do change of variables and rename T as 3 times Z for some Z integral in Z3. And then when we replace that K is 69 plus all of 3 to the 4th, and the T is 3Z, we get that 0 is equal to some power series in Z. And now on this example, Strassmann's theorem requires that coefficients of your power series converge to 0 as we approach infinity. That would be the case certainly, because since T is 3Z, then T to the n will be 3 to the n Z to the n. So this will go to 0 in triadic topology. And then we consider the smallest valuation at 3 of all coefficients. So the valuation at 3 of the first coefficient of the first coefficient is 2. So this is divisible exactly by 9 and not by 27. This one is also divisible exactly by 9 and not by 27. This is divisible by 243. And all the others are divisible by at least 81. So the smallest valuation is, well, the smallest divisibility by 3 is divisibility by 9, and it appears here and here. And then Strassmann's theorem says, take the largest coefficient where the smallest valuation appears. So it's a bit tricky to say, but so the smallest valuation is 3 squared, and take the largest amongst them. So this is the second one. And this number is the bound on the number of zeros. So in this case, there are at most 2 zeros. And then we know that there are we know that there are 2 rational points in the residue disk of 0, 1, because -3, 1 is in the same residue disk modulo 3. And then the same is true for the other residue disk 0, -1. So we get another point -3, -1. And similarly, we need to consider residue disks of infinity points, and we prove that there are no rational points in them. So there are at most 1 in each of the infinity residue disks. So we conclude that the number of rational points is at most 6, and we already know 6 points. So the number of them is exactly 6, and these are all of them. And unfortunately, none of them correspond to a 5 rational periodic point, so no such points exist in this case. But so this was just a motivation. I hope that, well, the principle of the method of Chabauty and Coleman is a bit clearer with this explicit example. Are there some questions now? No. Okay, then, well, I will continue with this. So then we recall that if C is sharp, then it means that we know its set of rational points. And sometimes the curve cannot be sharp. And for example, the theorem by Michael Stoll improves the theorem by Coleman, by saying that if we know that rank is strictly less than G minus 1, so Coleman required rank less or equal to G, and if it is a bit smaller, and then again we have some bound on P due to Strassmann's theorem, then the number of rational points can be bounded by the number of points over Fp plus 2 times R, where R is this rank. And as a corollary, we have that we have a nice statement about sharp curves of genus at least 2. Then the rank of its Jacobian is exactly G minus 1, because a priori we know that it's only less than G, but if it is strictly less than G minus 1, then this bound will be violated. And it's not possible. So we conclude that R will be exactly G minus 1. And this is one more reason why sharp curves are interesting. And in general, for the area of rational points, the relation between rational and p-adic points is still under research. And since I was a master student, I was motivated to construct families of sharp curves. So this is finally something that that is my research. And one of the goals that I had in past was to construct sharp curves of genus, well, 2 and larger genus. So I will explain some basic ideas how we can construct families of sharp curves of genus 2. And since we specified G equals 2, then the bound is pretty clear. And the idea is so that for that two residue disks have 2 points and all the others to have 1 point, for example, then this bound will be satisfied. So if each FP point lifts, how to say, to 1 rational point, and 2 of them lift to 2 points in CQ, then this is precisely this condition. Well, this is precisely the equality here. And of course, we want to use, we don't want to use many residue disks for it, so we will try to use a small number of them. And then this is some modular arithmetic. So this polynomial is not random. For example, if we want to consider curves, hyperelliptic curves of genus 2, well, all of them are hyperelliptic of genus 2, then it's given by polynomial f of degree 5 or 6. And if we consider degree 5, then by little Fermat's theorem, we know that x to the 5 can give residues 0 or plus or minus 1 modulo 11. So prime 11 is not an arbitrary prime. This is picked on purpose because then we can easily control polynomials, some polynomials of degree 5 modulo 11. And number 9 is chosen because 8 and 10 are not residue disks modulo 11. Are not, sorry, quadratic residues modulo 11. So the only way that this can be a square modulo 11 is when x is divisible by 11. So in this case, we get the number of F11 points is 3, 0 plus or minus 3, and only 1 infinity point because we are in odd degree case. So that was the idea behind this polynomial. And we conclude that the number of rational points cannot be greater of 5 if the rank condition is satisfied and 11 is a prime of good reduction. And the idea is then to, well, the easiest way will be to keep points with x equals 0 rational. So we will change this polynomial, but it will stay the same modulo 11, and still the free coefficient will be a square. So if it is not 9, then it will be some other square that is congruent to 9 modulo 11. and to add 2 more points inside these residue disks. Where am I? No, sorry. Oh, and for example, if we consider curves given this way, so just x to the 5 plus 11x to the 4 plus 11k plus 3 squared for some case that I will say about case later. The main thing is that, of course, well, we have some obvious rational points as when x is 0, as well we noticed on the previous slide, we get 2 points plus or minus 11k plus 3. And also we have one easy 0 of this polynomial that is minus 11. So we constructed 2 more rational points. And in this case, we see that we have at least 5 points on CK. And the same for another case. And these cases are all values less or equal to 50. So from 0 to 50, such that this curve has rank at most 1. And well, as we recall, it implies that it is exactly 1. So this is the first case. The second case is, well, similarly, we have, again, 0 and minus 11 as a root of this polynomial. So we have 5 points, and we can determine them if the rank is equal to 1. I added this second condition, although I didn't introduce it before. If the Jacobian of a curve is not absolutely simple, that we can factor it, and we have an easier way to find rational points on these curves. So then it would make these examples pointless in some sense if this is not the case. So that was the reason why one should check it, but I don't want to talk about it right now. And this motivates some very difficult questions that I would like to tackle somewhere in the future, because it's especially an attractive area these days. Because one should hope, and that is definitely my goal, to construct an infinite family of sharp curves. So what bounded me was that well, computer system, well, Magma can compute only up to some bound for this k, and well, that was for expository purposes from 0 to 50. So if we want to prove that, for example, this family has infinitely many curves of rank 1, then we need to use some other method and to bound dimensions of Selmer groups of these curves. But this seems to be difficult because number fields, if we consider number field obtained by this polynomial, it's quite complicated. It's degree 5, but still quite complicated. So the first question is, are there infinitely many k for which the rank of the Jacobian of any one of these 2 curves is 1? That would be something interesting, at least for me. And as we could notice, we can change this polynomial. So for example, we keep points 0 and minus 11 and plus and minus these 2 values. But also in the example, h of x was x cubed. So this is x times x plus 11 plus times x cubed. Of course, we can replace x cubed by any polynomial, any cubic polynomial that reduces to x cubed mod 11. So in this way, we can construct more potentially sharp curves. And then maybe because we allow more freedom, maybe in this family, there will be a way one day to prove that there are infinitely many, sorry, this is h, distinct polynomials h, such that this hyperelliptic curve has rank 1. And one thing to notice, if h has an integral 0 that is not 0 or minus 11, then we would find 2 more rational points. So then the curve would be excessive, and the rank will not be 1, will be strictly larger than 1. So this is not something we want to let to happen. And this is, well, this concludes this section on some family of sharp curves of rank 2. And then I wanted to say some examples that attracted my attention. Also that, for example, what can be the smallest number of rational points of a sharp curve? And it's, if we can maybe be a bit faster, so then we can see that the number of rational points will be at least 3. And this is a curve that has exactly 3 rational points, and proven by Chabauty-Coleman method that the set of rational points consists of these 3 points. Oh, sorry, then I talked, well, I don't know, do you usually have a break? Or no? Okay, then I will continue.
In any case, we have just 15 minutes,
Yeah.
so no sense for this question.
Yeah, sorry. And this is, if, well, for example, sharp curves can, and excessive curves can improve lower rank bounds in magma. For example, if we want to determine the rank of the Jacobian of this curve, there is a command in magma that give you a lower and upper bounds. And in this case, we can see that the lower bound is 0 and the upper bound is 2. For upper bounds, it uses this bounds on the Selmer dimensions of Selmer groups. And for the lower bounds, it uses, well, a search if we can generate enough linearly independent elements of the Jacobian, but for some reason, magma failed to do that in this case. And this curve has only 1 point modulo 5 and has at least 5 rational points. So the Coleman bound is violated, so the curve is excessive, and it means that the rank has to be at least equal to its genus, which is 2 in this case. So in this case, well, we can help magma to conclude that the rank of this, the rank of the Jacobian of this curve is 2. Okay, then maybe we can go to a bit to advertise more rational points on curves, and to say that sometimes we want not just rational points on curves, but points over some number fields. For example, the same principle is valid for the torsion of elliptic curves. And this is here. So if we want to study all potential subgroups of elliptic curves defined over a number field L, we want to compute rational points. We want to compute points on x1n of L, so not Q. And sometimes we x1n is also a curve that has a large genus. So sometimes we use some other modular curve x0 n, and usually we compute rational points over number fields of this curve. But the same principle holds. So we want to compute points x1n of a number field L, and there is a way to compute all of them together. So well, we now go back to this slide. There is something, well, there is a symmetric power of curves that is, if we just take d copies of a curve and then all permutations of the same points are the same. So this is a quotient by the symmetric group as d. It means that we consider all effective degree d divisors on X that are Q rational. So this is these are points on XD, and explicitly it states that the points X on XD are exactly sums of d points of which are not in Q, but they are fixed by all elements of the Galois group of Q. And we see that if we can determine the rational points of degree d on some curve X, it means that we know all points X of L for all degree d extensions. Because if we have a degree d extension, then we just take one point and all of its Galois conjugates, this will form an element of xd of q. And this is why symmetric powers of curves are so important. For example, we use them to extend Mazur's theorem to a number of fields that are not q. And also there is another motivation to do so. So we can use them to prove modularity statements and the extensions of modularity statements, well, from Wiles and other mathematicians from Q. So Freitas, Lehong, and Sixek used, well, information on quadratic points on certain curves to prove that elliptic curves over real quadratic fields are modular. And then this is extended to the totally cubic real fields, and nowadays, recently by Box, to elliptic curves over quartic fields that do not contain square root of 5. And there are different techniques to compute points on symmetric powers of curves, and one of them is symmetric Chabauty. And luckily, well, we have seen Chabauty now. So as a heuristics, well, it's similar. So again, if we have something of, this is something of dimension G, so JQP has dimension G, this now has dimension D, so this is D power of curves. And here we have some submanifold of dimension at most R. And in this case, we want D plus R to be at most G to hope that their intersection is finite. So then the Chabauty condition in this case is R plus D is less or equal to G. And we can see if D is 1, that this is exactly the Chabauty condition. And the strategy is similar. So we again obtain a subspace of vanishing differentials. And in this case, it will have dimension at least D, because we want this condition. And then we have a D, at least D linear relations on a D dimensional subspace. So then that is our hope to get something finite. However, well, maybe it's just, maybe we can notice that in this case, we don't have finiteness all the time. And if we consider any hyperelliptic curve, then for any rational number, we consider the divisor x naught and square root of f of x is naught and its conjugate. So this is fixed by Galois group of Q, and hence this is always a quadratic point. So hyperelliptic curves will always have infinitely many quadratic points. And this number of, if symmetric power of curves has infinitely many points, then it's related to its gonality, so the map of the least degree D map to the projective line. And maybe, so this is what we see. If there is a map to P1 or to an elliptic curve that has infinitely many rational points, and this map has degree at most D, then the set of D symmetric points is infinite. There is some other condition that I will skip. And then if we want to study symmetric points on symmetric powers of curves, we have first to describe all infinite subsets of them, and then to find the finite set of isolated points. And how do we avoid this infinite subset? So if there is a map of curves that induces infinitely many points, then we need to impose some condition on differentials, and that's that we only consider differentials that have trace 0 with respect to this map, because then these differentials don't see curve C that is a source on infinitely many rational points. And then we use only differentials that have trace 0 to determine the finite set of isolated points. So that is some idea. And so this is, for example, why a concrete example is that, as I said, so the classification of the finite groups that could be torsion subgroups of elliptic curves defined over cubic number fields are computed last year, and for that they really computed some cubic powers of some rational points and cubic powers of curves. And just to say what was the starting point of our work is that if we consider one concrete curve, we don't need to know its equations. X naught 65. It has 4 rational points, and it has a map of degree 2 to the elliptic curve of rank 1. So the set of quadratic points is infinite. And we can say more precisely that set of quadratic points comes as a pullback of infinitely many rational points on this elliptic curve plus sums of cusps. So these are sums of rational points. And what was unknown previously, how to determine larger powers of curves. So how to determine cubic points on this curve if we already know that the set of quadratic points is infinite. For example, so if we take any rational point on x naught 65, then we add this point plus all quadratic points is an element of cubic power. So we have infinitely many points here as well. And then we needed a criterion that handles this case. So how to determine cubic points on curves that have infinitely many quadratic points, or in general, just replace D and M such that M is smaller than D. And this is a theorem that is supposed to handle this. Let's see, and that I will stop after that. So in this concrete example, let's assume that we have a map of curves of degree at most 3 and prime greater or equal to 11. And we have a basis of vanishing differentials of trace 0 with respect to this map. And we consider a cubic point on curve X. And then we pick up a well-behaved uniformizer at each of these points. Then we extend QP to contain all 3 points. Of course, this might be an extension of QP because these 3 points don't have to be rational pointwise. And we take any generator of the maximal ideal. So this is a uniformizer of this field. And we expand all differentials as we did for the usual Chabauty-Coleman method. So this is just expansion of omega j at Qi. And then assume the degree of this row is 2. And assume that Q1 plus Q3 is a pullback of something from C. Then if this matrix, so these are coefficients of omega 1 and omega 2, these coefficients. So if this matrix has rank 2, then we conclude that all maps in the residue disk of Q are of the same shape. So let's recall that we started with a point that is Q2 plus a pull, Q2 plus here. So Q is Q2 plus a pullback of something, then all points inside of this residue disk have the same shape. And that was the theorem we proved. Well, we have distinct cases. I will skip the proof. So there are some distinctions, but this theorem, and there, for example, maybe not so interesting, this is how we get it. For example, if we specify a point, we compute the matrices and conclude that matrices have rank 2, and then we obtain that all points here are of the same shape. And just to summarize results, so we use this technique and Mordell-Weil sieve to compute cubic points on these 6 modular curves and quartic points on x naught 65. And for example, x naught 65 doesn't have cubic point, well, truly cubic points unless the cubic field is this one. So for all other, we don't have a 65 torsion, an elliptic curve over that cubic field with a 65 torsion, and that is something interesting, I think. And maybe yes. So I will not talk about non-abelian Chabauty. I will stop. And thank you for your attention.
Thank you very much, Stevan. Do we have any questions or comments? If not, then I would like just to say that subject is very interesting, but we are the beginner in this field. And maybe for us, it was better to concentrate on some concrete problem and to understand it in details, because all these integrals and reduction and so on, maybe it was too much for us. But in any case, it's clear that this is a real science. So quite advanced tools and so on.
Okay, I'm sorry about that.
The integral was quite surprising and interesting to me. Thank you.
Thank you.
Okay, so thank you very much. See you soon.
Oh, thank you. See you. Спасибо.
Thank you.